Hey guys, today we are going to talk about potential and kinetic energy. So we'll get started. Kinetic energy is going to be your energy of an object in motion. So any object that is actually moving at the time of the measurement has kinetic energy. Kinetic energy is abbreviated as a capital A, capital E. It is a scalar quantity, and the unit for that is a joule, which joule is a capital J, would be the unit you would put in. And if you remember that, that is also the unit used for work. So these two things will come together. With kinetic energy, the more mass something has, the more kinetic energy it will have, which makes sense if you look at your formula, right? So we have mass times velocity is kind of the meat and potatoes of that formula. So if you increase the mass or you increase the velocity, you're going to end up with a higher kinetic energy. Example of this, we have a pretty simple example here. John ran 18 kilometers in 1 hour. If his kinetic energy was 694 joules, what was his mass? So we know what we're given. We have his the distance, we have the time, we have the kinetic energy, and we need to find his mass. So first, we're going to have to find the velocity because we know our kinetic energy formula is here. We have the kinetic energy, we have its mass, but we don't have velocity. So we are first going to have to figure out what velocity is. So we're going back to kind of towards the beginning of the year with this formula. So we know velocity is distance or displacement divided by the time. In this case, we're going to have 18 divided by 1 to give us kilometers per hour. So we're going to have 18 kilometers per hour. Velocity has to be in meters per second. Okay, it's been that way all year. So once we calculate velocity, we need to convert that into meters per second, which is going to give us 5 meters per second. Now we have all the variables that we need to substitute into this formula, so we're going to do that. We're going to sub in the 694 for the kinetic energy equals 1/2 times the mass times the velocity, which is 5 squared. We are solving for mass. Again, you can rearrange this formula in the beginning to solve for mass if you'd like to do that, or you can just solve for that missing variable. So we're going to break this down and solve it, and the mass of this person is 55.5 kilograms. And we knew all of that just based off of the kinetic energy and how long it took him to run a certain distance. So a quick reminder, we already know these formulas from previous chapters. We just talked about work. We know that work can also be mass times acceleration. So this one's kind of a throwback. This one was from our two-dimensional motion unit. So this is unit 2. But we do have the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times the distance. So we can substitute those together to derive our own formulas to find an equation for work. So we know that acceleration part is part of this formula. It's also part of this one. So if we set this equal to A and then substitute that value in, we can substitute that in there for work. So we should have work is equal to mass times the final velocity squared minus the initial velocity squared over 2. Then we come to the work kinetic energy theorem. Okay, so we talked about this a little bit before, how the work was going to come into play here. So the work kinetic energy theorem says that the net work done by all forces acting on an object is equal to the change in that object's kinetic energy. Okay, so if you know the change in energy, you know the net work done, and vice versa. So if you are able to calculate how much work was done, you also then know how much kinetic energy has happened. So that's why they both have the same units. They're both measuring the same thing. So if you have this picture here, you have this person swinging a hammer, and he is moving the hammer, and he's creating kinetic energy by moving the hammer. So the hammer can do work on the puck there. So when he hits the puck with the hammer, he's applying force downward. The puck is also moving downward, so that is the work. And then that basically goes through a pretty simple machine here with some levers and causes the puck on the other side to rise to ring your bell. So if you were able to figure out, back in this picture, if you were able to determine the kinetic energy that was created here, you could then figure out how much work was done. So another example, we have Ellie and Leah push a 90-kilogram cart across a field. After it is pushed a distance of 6 meters starting from rest, its speed is 10 meters per second. So what is the magnitude of the net force on the cart? So what are we given? We have the mass, we have the distance, we have the velocities. So we are starting from rest, and then it gets up to a speed of 10. So we're going to say that our initial velocity was 0 and our final velocity is 10. We need to figure out the net force. Okay, so what do we have? We have these two formulas. The first one does not include force, right? But we can determine work from that. And the second formula is going to give us force. There's force involved, but we would first have to have work and distance. So what you can do is you can derive your own formula for this, or you can solve the first equation and then substitute that information into the second. So I chose to do it that way for this example. So here I have work is equal to the mass in kilograms times your final velocity minus your initial velocity. This is squared. And then this is all divided by 2. So I guess that's let me see, initial velocity, final velocity. Yeah, this should be squared. This should be 100. So that would make this a little bit bigger, but let's see.